So, thank you. I want the title to, oh boy.
Good. Hit this. Just pointer.
Okay, thanks. Good. So I wanted the title to be a little intriguing, checkpointing a subsystem remotely. So what I'm going to talk about is I'll just briefly review DMTCP. This is for checkpointing, transparent checkpointing in this case, so you don't have to modify your application at all, and it requires no admin privileges. It just works with user software directly. And then I want to talk about a new paradigm, a general way of using proxies to extend the power of checkpointing. And I'll give two major examples there. So first, let's review DMTCP. So DMTCP has been going on for almost 15 years now. It's widely used. Maybe for this audience, one of the more interesting applications would be if you are running in batch and you got a 12-hour batch time slot, only your job takes 18 hours. Hopefully that sounds familiar to many of you. This Slurm, of course, can, or whatever resource manager can send you a signal when time's about to elapse, but then it's up to you to figure out what to do when time is about to elapse. So with transparent checkpointing, it's easy, and it's very easy to hook that up. So in my group, there's one central question which has really intrigued us for many, many years now. What are the limits of checkpointing applications in the real world? So, originally people would say, okay, we're in a cluster, but it's okay, we're just going to use the CPU and nothing else. So things were relatively nice. Now we have all these accelerators, we have various other system services. How are we going to support those with checkpointing? So our original answer from earlier work was basically the idea of process virtualization. So the first thing you see when you try to extend to the real world is the real world has all of these ugly little IDs that are expected to be persistent. The real world does not expect that the real world will be suspended or killed and then the real world will be restarted later. The real world will not take kindly if you ask it, please use the original IDs in the previous real world. So the solution that we had basically was to interpose on all system calls or library calls that might refer to those IDs. And roughly the motto was never let the application see a real ID. Always hide the ID from the application. A lot of that work you'll find in the thesis of one of my former students, Kapila Arye, and then an extension by Jiajun Cao, who showed how to also transparently checkpoint InfiniBand with no privileges. And that turns out to be quite a trick since the API is quite complex. And then, of course, we demonstrated there actually is a variety of authors, including authors from this lab here, the Mbappage team, showing how to checkpoint over 32,000 cores. To the best of our knowledge, that's still 100 times larger than anything else that exists in the literature in terms of transparent checkpointing. Okay, so now let's talk more about the future. So we said that we want to look at what are the limitations in the real world. Well, the next limitation we want to look at is, let's take two examples that were considered hard. One would be checkpointing CUDA, or GPUs in general. And the other one would be, in the case of NERSC, they asked us to checkpoint Cray MPI there over the GNI network. And there was no way we want to extend our work to then support the complex API of the GNI network. That would be a lot of work. So let's look at what we did. So I have this tendency to tell the whole story of the entire talk early in one of the slides, and then I'll just go through the rest of the slides very quickly, saying you already saw it. So knowing my own personality, I decided to just play to it directly. So here's the slide which tells you a lot of the story right there. So initially, let's take CUDA as our example, and we'll show the idea of how proxies are supposed to work. So initially, we would have an application with a CUDA library built in, talking to the GPU device. It's very simple. And the only problem is when you want to checkpoint, where are you going to cut the line? You cannot checkpoint that GPU hardware. It's one of these limitations of the real world that we were just talking about. The real world is often unkind. So our solution is we split the application into two processes, and then we know exactly where to cut it, and then to checkpoint only on the right. So we'll split that into an application process. Well, I think I reversed it, but the application process should be on the right, and the proxy process should be on the left. So the proxy process will be using the CUDA library to talk to the GPU. The application process will have a fake CUDA library just to make the compiler happy, but we're never going to use it. We're always going to interpose whenever the application tries to call that CUDA library, and we're going to send it over to the proxy process to do the actual work. Okay, so the game is clear. When it's time to checkpoint, we can throw away everything on the left. We're just going to save the application process all the way on the right. And since the application process has no hardware and it has a dummy CUDA library that we will never use, it's all going to work. So here it is written out in text. So the system services here are clear. It's the GPU and the CUDA library. Solution is we split the user process into two. We have the system service requests. These are passed from the application process to the proxy. And then checkpoint time, the proxy can be disconnected. Or if there's a crash, the proxy process is gone forever. We're not going to try to save it. We will only save the application process. So we are saving the state of the application process. And then when it's time to restart, we'll just bring up a completely new proxy, and basically a completely new real world that knows nothing about the old real world. And this new proxy, well, we'll just give it a few simple commands to put it in the same state that it used to be. So if there was CUDA memory that was malloc, we'll malloc that same CUDA memory. But usually that's a very short list of commands just to bring the proxy up to date. Okay, good. And as I note at the bottom, the idea of proxies has been used for a long time, for example, in checkpointing VNC sessions. But here we want to propose it as a general paradigm. Okay, so now we're back to the old slide. It's the old saying that first tell them what you're going to say, then say it, and then tell them what you said. So hopefully the idea is clear. I have the same mistake on the right. The application process should be the one all the way to the right that has the application in it. And the proxy process is the one that has an active CUDA library. So ideally, the game is clear. Let's see how well it works in practice. So we did some experiments with this, and this will appear now in IEEE cluster in September. So first of all, just a bit of advertising, since one of our co-authors is from NVIDIA, Mike Sullivan. The number of GPUs used in the top 500 continues to rise. So hopefully that motivates what we're trying to do here. Okay, and then there was previous work in checkpointing CUDA programs, only the trouble is those methods don't work anymore. They stopped working. They stopped working as a CUDA version 4 in 2011 because that's when they introduced zero-copy transfers and CUDA managed memory, and the old approaches just weren't up to it. So here's a timeline of how the checkpointing has gone. So we see 2009, they succeeded in checkpointing CUDA. 2009, different way of checkpointing it. 2011, yeah, let's do it again. 2011, now let's do it for OpenCL. Then 2011, NVIDIA announces we're going to switch to CUDA 4, managed memory, zero-copy transfers. Whoops. And then there's no more progress all of a sudden. That's it. 2013, CUDA 6, still no more progress. 2016, CUDA 8, still no progress. In 2016, one group went backwards in time and said that they still can't handle the managed memory, but at least if you don't use the managed memory that modern CUDA provides, then at least they can make the old style work. So this is the first checkpoint restart system that does handle the managed memory, zero copy, UVM, all of that, all of the good stuff. And this is roughly analogous to using virtual memory in a modern operating system. Very few of us would want to say, okay, if you're using too much memory, you're going to have to swap some memory in and swap some memory out, and you write the code for that yourself. You really want to use virtual memory. And UVM for CUDA is playing the same role there. So I would anticipate in the future that will be used more and more widely. Okay, so in any case, I'll skip this for the sake of time, but ultimately the trick was to do use shadow pages, and then we get a free benefit. In the second bullet, we found that we could also then do a very fast kind of checkpointing, forked checkpointing. With forked checkpointing, it means that our application process, when it's told to checkpoint, it can simply fork a child and let the child write out everything from memory to disk, and the parent continues computing. So you get to overlap checkpointing with a continuing computation. Okay, so first set of numbers. So these are runtimes. For almost each one of those graphs, you have to read it carefully to figure out what it's actually saying. But the one on the left, Rodinia does not use zero copy transfer. It doesn't use managed memory. So this is just to show that we're up to state of the art for the past. Then the next two are applications that are HP GMG and Cray are well-known applications in the real world. We're operating with 4 Tesla P100s per node. We're using CUDA 8. So HP GMG, all the benchmarks use these unusual units of those, let's see, DOFs. Basically, it's kind of speedometer, how many miles per hour you're getting. And so the idea here now is what we're seeing is percent overhead compared to native performance. So we're seeing percent overhead of like 6%, it's going up to 10%. But by the time that we go to 4 nodes with 8 MPI processes each, we're back down to 8%. And at that point, the facility we had couldn't provide us with more nodes than that. Cray, so there again, you have to read it carefully to see how to interpret it. But there we're talking about native versus our system. And those vertical bars are reasonably close again. They're within that 6% or so overhead. Okay, and then there's the checkpoint restart time, which is good. And again, in the interest of time, let's just move on. So, and then we come to the second example that I want to discuss. This one is still in progress. So MPI over the Cray GNI or Gemini network using proxies. So here I set up my own saying, if you have a hammer, then make MPI look like a nail. So the idea is our hammer is proxies. So let's see if we can apply them to MPI. So why is this interesting? Well, at NERSC, they're using Cray MPI as their strongly preferred MPI. It's been enhanced especially for the Cray architecture. So plus they have this GNI network that I described, so it's similar in spirit to InfiniBand, but the API is completely different. And as I said, so we weren't eager to do a lot of work just for this one architecture. We wanted to use general principles. So the idea of proxies then is that we're going to look at what are the services provided by MPI. Well, MPI provides us with ranks, communicators, groups, topologies, and so on. Okay, so let's have a proxy manage those services for us. So again, if you recall the picture we started with, so now instead of a CUDA library, this will be an MPI library. And on each node, we'll have one of those MPI libraries talking to, and instead of the GPU, this will now be an MPI network. And then it's up to the MPI service to transport over that MPI network, which in this case happens to be using GNI. Okay, so moving back to what we're discussing. So with proxies now, the GNI network is completely hidden. It's just part of the system service being provided to us by MPI. So that we don't need to support GNI. We don't even see it. We know nothing about GNI. We're isolating the application completely from the rest of the MPI service. Interestingly enough, in principle, this means we could actually checkpoint that Cray MPI GNI over on Cori at NERSC, and then we could, in principle, restart here on MVAPIC MPI with InfiniBand here at the Ohio Supercomputer Center. And that should work fine, because all we're using is the API to MPI. So I did bring MVAPIC back into it. I wasn't going to talk only about Cray for this part. In any case, so this is another example where there are interesting ideas to be found by exploring the idea of proxies, and we're continuing to look at other possible cases for proxies. Okay, so I think that concludes. Any questions?